This screencast is going to look at how to run multiple regression analyses. This is where we are trying to predict values in the dependent variable using several independent variables. In this screencast, we will look at three different methods of multiple regression. We will look at the direct method, where all independent variables are entered in the same stage of the regression equation. We will also look at how to run a hierarchical regression, where we enter the independent variables in different blocks. And finally, we will look at how to run a moderated hierarchical regression, where we can look at the interaction between two independent variables. This screencast will not cover the assumptions of regression, so if you're interested in how to test and satisfy the assumptions of regression, please see Multiple Regression 1 or consult a statistics textbook. The first type of multiple regression we're going to look at is going to be the direct method. Here we're going to look at how to enter the variables into the regression equation, and we will enter all variables at the same time to try and identify which out of the independent variables is the best predictor of our dependent variable. In this example, we are going to use data from an experiment which explored the best predictors of speed in tennis players. The independent variables were the number of years' experience of playing tennis, upper body strength, and coordination. To run the regression, we are going to go to Analyze, select Regression, and then choose Linear. In this analysis, as we are trying to predict speed, I am going to select this and move it into the dependent box. Next, I'm going to select all the independent variables and move them to the independence box. In this method, the direct method, I need to ensure that the method selected is Enter, as this will make sure that all the variables are entered in the same stage of the regression analysis. Next, I'm going to select Statistics. Of these options, I'm going to select Descriptives, which will give us means, standard deviations, and correlations in between the independent and dependent variables, and also confidence intervals. Click Continue, and then OK to run the analysis. The output shows us first the descriptive statistics, so the mean and standard deviation for both the dependent and all of the independent variables. In the correlations table, we can see that all the independent variables are positively and significantly correlated with the dependent variable of ball speed. The highest correlation is between upper body strength and ball speed. There are also significant and positive correlations in between the years of tennis experience and upper body strength, and also hand-eye coordination and body strength. However, the correlation between hand-eye coordination and years of tennis experience is not significant. These values are important as they help us satisfy the assumption that the independent variables are not strongly or perfectly correlated. As all the Pearson's correlation values are below 0.9, we can be satisfied that we have met this assumption. The R-squared value in the model summary tells us that 70.5% of the variance in ball speed can be predicted by hand-eye coordination, years of tennis experience, and upper body strength. However, it doesn't tell us whether this amount of variance is significant, nor does it tell us which of the predictors is the best variable to predict ball speed. The adjusted R-squared is useful when we have several predictors, as in our case. As more independent variables are added to the regression model, the standard R-squared will often increase, but it will never decrease. To compensate for this, the adjusted R-squared can go up or down depending on whether the addition of a new independent variable does or does not add to the explanatory power of the model. So for example, if we added an extra variable to this direct method regression, the r squared will probably increase. However, the adjusted r squared may decrease. This would indicate that the new independent variable does not add to the explanatory power of the model, so may not be an important predictor. To see if the model significantly predicts the variance in our dependent variable, so ball speed, we need to look at the f value in the ANOVA table and its respective significance value. In our example, the f value is 28.68 and the significance is below 0.05. Therefore, we can confirm that our independent variables significantly predict the variance in our dependent variables. However, again, we still don't know which out of the variables is the better predictor. In the coefficients box, we have both the unstandardized and standardized coefficients. The unstandardized coefficients show how much one unit change in the independent variable predicts the dependent variable, using the unit scores in which these variables have been measured. However, in certain cases, as in our example, the different independent variables are measured in different units or on different scales, so the predictive effects are difficult to see using the unstandardized coefficients. Therefore, to compare the different independent variables, we would use the standardized coefficients. The standardized beta coefficients show us both the strength and the direction of the prediction from the independent variable to the dependent variable. If these values are positive, it means that the independent variable predicts an increase in the dependent variable. If these values are negative, it indicates that the independent variable predicts a decrease in the dependent variable. We also want to look at the significance values, and if these values are below 0.05, then we know that the independent variable significantly predicts the dependent variable. So in our example, we can see that all three independent variables are significant and positive predictors of ball speed. However, if we look at the standardized coefficients, we can see that the coefficient for upper body strength of 0.4445 is a much larger predictor than both hand-eye coordination at 0.39 and years of tennis experience at 0.28. Therefore, we can say that the best predictor of ball speed in this sample is upper body strength. The 95% confidence intervals show us that if we were to draw randomly 100 samples from the same population as we have measured here, in 95 of these samples, the unstandardized coefficient for each of the independent variables would be between the values reported in the lower and upper bound boxes. Now we're going to look at how to run and interpret a multiple regression analysis using the hierarchical method. This is where we enter the independent variables in different stages of the regression equation, and we can see how much a variable predicts variance in the dependent variable over and above that of the other independent variables. Hierarchical regression analysis is often used when we have a prior theory or hypothesis that one predictor variable should predict the dependent variables before the other predictor variables. Also, we may use this method when we know that one variable predicts the dependent variable very strongly, but we want to see the effects of other variables when this strong variable is taken into account. So in the example we have just used, it may be that we want to take into account how long someone's been playing tennis, so their years of tennis experience, and simply look at the effects of upper body strength and coordination over and above the effects of their tennis experience. So using the same data as before, we are going to go to Analyze, select Regression, and then select Linear. As we are trying to predict changes in speed, I'm going to move this variable into the dependent box. Next, I'm going to select years and move it into the independence box. This is going to be the first block of variables which I'm going to enter into the analyses. Now, I'm going to click Next. This is going to allow me to add in the remaining variables of strength and coordination in a different step to years, and will then in the output show how much they predict changes in speed over and above what is predicted by the years of experience. Now you can see that the independence box is again empty as we've moved into a new step, so I can now select strength and coordination and move them to the independence box. Now I'm going to click Statistics. In the Statistics box, I'm going to select several options. First, I'm going to select the R-squared changed button. This is very important in hierarchical regression, as it shows us the change in the amount of variance explained from one step to another. So in this case, it will show us the amount of variance explained for years experience, and then it will show us the change, and so the increase of variance explained by strength and coordination over and above that is explained by years. I'm also going to select descriptives, as this will tell us information such as the means for each of the variables and how they correlate with each other. Finally, I'm also going to select confidence intervals. Then click Continue, and then OK to run the analysis. Again, the first box on the output is the descriptive statistics, so the means and standard deviations, as well as the correlations between the independent and dependent variables. And as you can see, the relationships between the variables in terms of the correlations are unchanged when using the hierarchical method as opposed to the direct method. It is just the way which we use the predictions in the regression model that we changed. So we wouldn't expect any changes in the Pearson's correlations or the respective significance values based on the different methods. When interpreting the output of a hierarchical regression, the values we are most interested in the model summary is the change statistics with the R-squared change and its respective significance value. The R-squared change value is the amount of variance explained by that step in the model. So for the second step in our model where we entered the second two predictors, the R-squared change value shows us the amount of variance that they explain in the dependent variable over and above the amount explained by the first independent variable entered in the first step of the model. So in our example, the first R-squared change value of 0.29, which is significant as the significant F value is below 0.05, tells us that years experience explains 29% of the variance in ball speed. When we look at the second step of the model, this R-squared change value of 0.42, which is also significant as the significance value is below 0.05, tells us that hand-eye coordination and strength explain 42% of the variance in ball speed over and above the amount already explained by the years of tennis experience. If we look at the R-squared value, we can see that for the first step of the model, the R-squared change and the R-squared value are the same. This is the first step, so we don't have an increase in R-squared, we just see how much variance the independent variable accounts for in the dependent variable. The second R-square score is much larger, and this is as it's a culmination, a total, of the two steps of the model. So it's the 0.29 from the first step of the model, and then the R-squared change value of 0.41 from the second step of the model. These values are added together to show the total amount of variance explained by all the independent variables. So in this example, the independent variables account for 70% of the variance in the dependent variable. As we can see, the change statistics F change value and the F change value in the ANOVA test for the first step of the model are both the same, 15.501. However, for the second step of the model, the two values are not the same. The F change in the change statistics is 25.337, and for the ANOVA test, the F is 28.676. This difference is because in the model summary and the change statistics, the value is testing the R-squared in the second stage of the model, whereas in the ANOVA table, the value is testing the change from step 1 to step 2. This is why for the second step of the model, the F values in the model summary and the ANOVA tables are not identical as in the first step of the model. By looking at the coefficients box, we can see the contribution of each independent variable to the explanation of variance in the dependent variable for each stage of the model. So in the first step, we can see that years of tennis experience has a standardised coefficient of 0.54, which is also significant. So this is a significant predictor of ball speed. However, when we look at the second step of the model, where we added in our second and third independent variables, we can see that the standardised coefficient of years of tennis experience is still significant, but the beta value has dropped to 0.28. And we can see that both upper body strength and hand-eye coordination are stronger predictors of ball speed as they have larger standardised coefficients. The best predictor is upper body strength with a beta value of 0.45, which is significant. If we were writing up our results, this is how we report our findings of the hierarchical multiple regression. For each independent variable, we would note the standardised coefficient, so for example for upper body strength this is 0.45, and also the significance or p-value. If, as in our example, some of the significance values are reported as 0.000, we would report this as p is less than 0.001. This is because the value does not equal 0.000, it is just simply too small to display on the SPSS output. It is also good to say within your results section which the best predictor was. In our example, this was upper body strength. We would also report the F value its respective significant value and the R squared for each stage of the regression model. For step 2, we could, instead of reporting the whole F value, report the F change value, so the difference in between step 1 and step 2, and we could also report the R squared change as opposed to the overall R squared. In the text in this example, I have included the overall F and the overall R squared. The final analysis we will look at in this screencast is moderated hierarchical regression. This is where we look at the interaction between two of the independent variables and how this might predict changes in the dependent variable. So we're going to look at how the interaction between strength and coordination can predict ball speed. First, we are going to convert the scores of the independent variables to z-scores. This is so that we reduce the correlation between these predictors and their interaction term. To do this, we go to Analyze, select Descriptive Statistics, and choose Descriptives. Here, we are going to select the variables which we want to examine an interaction between, so strength and coordination, and move them to the variables box. Next, we want to select Save Standardized Values as Variables, and this will save z-scores of strength and coordination as different variables in our spreadsheet. Next, click OK. And as you can see in the spreadsheet, we now have z-scores for each participant for both strength and coordination. So we have standardized values, which makes it possible to look at the interaction between these variables, which were measured initially on different scales. We now need to create the interaction between these two variables using the compute function. To do this, I'm going to go to Transform and select Compute Variable. First, I need to name my variable in the target variable box, so I'm going to type interaction in this area. Next, I'm going to move the z-score of strength into the numeric expression box. And to create the interaction, I want to times this score by the z-score for coordination. So I'm going to select the asterisk, as this will multiply the two values. Then I select the z-score for coordination and again move this to the numeric expression box. Finally, I click OK. And again, we can see that the interaction has been added as a new variable in the spreadsheet. Now that we have created the interaction term, we can now run the analysis to use this as a predictor of speed. So we go to Analyze, and then select Regression, and again Linear Regression. And as we are again trying to predict ball speed, I'm going to move this to the dependent box. And for the independent variables, I'm going to put the individual predictors, so strength and coordination, in the first step of our regression equation. So I select these and move them to the independence box. For this, it's important that we select the standardized values, so the z-scores for the predictor variables, not the initial raw scores for the independent variables. I then click Next so that I can add the interaction term in the next step of the regression equation. So I select the interaction variable and move this into the independence box. Again, I will select Statistics, and as with the previous hierarchical regression, I'm going to select R-squared change, descriptives, and confidence intervals. Next, click Continue, and then OK to run the analysis. When we look at the correlations, we can see that individually upper body strength and hand-eye coordination are significantly and positively correlated with ball speed. However, the interaction between these two variables is uncorrelated, with a low Pearson's correlation and the significance value being above 0.05. And when we look at the model summary and the change statistics, we can see that the R-square in the first step, so with the variables individually, 64% of the variance in ball speed is predicted by hand-eye coordination and upper body strength, and this is significant, as the significant F change value is below 0.05. When we look at the second step of the model, the interaction between these two variables predicts a very small but significant amount of variance over and above their individual contribution. So 5% of the variance in ball speed is significantly predicted by the interaction between upper body strength and hand-eye coordination. And when we look at the coefficients box, we can see that while the interaction significantly predicts changes in ball speed, that the greatest predictors in the second step is still upper body strength, and the predictions made by hand-eye coordination are still stronger than the interaction. Therefore, we can assume that upper body strength alone is the best predictor of ball speed in tennis players. That concludes the screencast for Multiple Regression 2. We have looked at how to run and analyse 3 different types of multiple regression using the direct, hierarchical and moderated hierarchical methods.